Okay, well, thank you for everybody joining. Thank you for Peter for being here with us. Dr. Peter Garrett is a retired hydrogeologist. He last spoke to us in Bryant about the peculiar geochemical relationships between the Old Town Water District supply wells and the Stillwater River. In a larger context, he considers the climate crisis to be the major challenge of our time, along with many others of us, obviously, in that way, speaking to the choir. He not only sees ways in which each of us can play a part, he also advocates for climate restoration. This is involving the removal of legacy greenhouse gases from the atmosphere and ocean as a necessary goal to get us beyond and in agreement with the Paris Accord. Which at one time, as he mentions himself, was seemed to be a reasonable goal, becoming farther and farther away. He also lobbies state legislators, and our members of Congress regarding effective climate policies. He's currently co-liaison to Senator Collins, along with Professor David Batuski at the Physics Department at our university, on behalf of the Citizen Climate Lobby. Thank you for joining us, Peter.
Well, thank you for introducing me, and thank you all for coming, whether on Zoom or here in this third floor room where we get a good view of the rest of the campus. So I'm going to start off here with a word that we hardly ever use: climate consternation. And this picture by Jill Pelto, who was apparently one of your students here, and her father's various graphs here. The red and pink and yellow graph is probably a temperature graph. The one below it on kind of the bottom right of this picture is sea level rise, presumably. It looks kind of wet. And the one on the bottom left is ice retreat that you are so familiar with. And so consternation is a word that we don't often use. And so I had to look up its dictionary, a definition. Feelings of anxiety or dismay, typically of something unexpected. And I'm sure you'll agree with me that all these things are unexpected, like killing heat waves. Heat waves so hot that just working outside even for a short while could kill you because the temperature is way above your body temperature. Floods so intense that you might be canoeing down Main Street. Droughts so intense that some people are leaving their farms, particularly in the global south, and migrating. Wildfires, hardly need to say any more about that. Storms and hurricanes bigger than ever, and sea level rise. This is not what we expected when I was a kid, and I imagine that you read that same way. Now, the Keeling curve we all know about. It was carbon dioxide was monitored in 1959, and from then on a monthly basis on Mauna Loa, where there aren't any other emissions to worry about. And obviously, it keeps going up. I was born off to the bottom left of this and didn't notice any of these changes, but I'm wondering whether this is our legacy that we leave. I hope it's not, but that's what I see now. This, of course, this graph came from the work done here at Orono and at others too around the world, and you can see it's climbing very steeply towards the end. This is obviously the last 1,000 years. And here are the gases that are the problem. Over on the left-hand side here, I'm using James Hansen's watts per square meter here as a kind of a temperature gauge. And you can see that carbon dioxide is the major gas, methane is next, and there are others on top. All seem to be increasing with time. And as we know, the major cause of this is the burning of fossil fuels. And the next one. So these are the simplified climate paradigms that we have. This is the one that basically we're brought up with. I mean, let's face it, we're all kind of hooked and addicted to fossil fuels, alas. And unfortunately, a major candidate for the presidency still thinks that this is the paradigm. Next one is burn less now, where kind of we are. And I'm going to propose a third one, which is maybe we can get back to some of the climate that we knew as children, and certainly our grandparents knew. So on to the next one, climate restoration. I hardly need to read through this, but the current state is 420 parts per million of carbon dioxide. We want to get down to somewhere near 300 and halve the concentration of methane. And that should bring us back to 0 degrees warming, not the 1.5 or 2 that the climate our policies have been. Well, I want to give you an idea here of the difference between the legacy carbon dioxide and the annual emissions. The legacy is much bigger than the annual, and it's the legacy emissions that are giving us our climate change. And almost all of our efforts for the Paris Accords are focused on that yellow square. Interesting, eh? So what have we been doing? Well, one is pricing carbon emissions. Some countries have gone in for this. In this case, in the US, we haven't gone in for it, alas, even though there has been a carbon fee and dividend, sometimes called carbon cashback, have been proposed, but we haven't gone that far. Also, removing subsidies. Can you believe this? The global annual fossil fuel subsidies amount to $1 trillion. As if there's not enough benefit given to them. We truly are addicted to that stuff. So what will happen when we get to net zero, according to the Paris Accords? Do you think it'll be like this? Champagne popping? Not likely, but that's what some people think it will be. What will it look like? It'll look worse. And that's because the big orange area of the earlier graph, which I'll show again in just a minute, is the cause of climate change. So here's what will happen to cumulative carbon dioxide emissions if we reduce annual emissions by 10% every year for 20 years. This should come up. Oh, here we are. So the annual emissions, the yellow dot at the bottom here, reducing a certain amount every year. And the cumulative is this other tall bar. And then over time, add the yellow to the red. That's what you get. It's not a happy picture. Luckily, I'm not the only person in the world to have thought that we need to take some action to remove carbon dioxide, even in order to get to the 1.5 degrees Celsius. So the Intergovernmental Panel on Climate Change in their 2021 report mentioned that. They are not alone. Jennifer Granholm, Secretary of the Department of Energy, says, yes, we need to do that, and here's some money to help us to investigate that. Also, Susan Collins, well known to many of us, often works with Senator Maria Cantwell in Washington, and here's the CREST Act that they got together, which is intended to provide some money to investigate the various technologies that would that remove carbon dioxide and other emissions. So it's not either or, it's both. And so emissions reductions involves getting a different source of energy. It also means reducing methane emissions, and it involves various techniques. Heat pumps are not included there, but we've heard a lot about those. EVs, electric vehicles, yes, for sure. And we also need to actually reduce atmospheric carbon dioxide. And how are we going to do that? I'm going to mention some of these things. Enhanced natural processes, carbon negative concrete, direct air capture. So here are some. On land first. You'll notice that the surround of these pictures is based upon where we are, and the land is green, you'll see. So photosynthesis, forest management is one of the things that we have to deal with, but the trees that we have in the boreal forests or the forests of the world have been greatly reduced over time, and they are actually not sufficient to take out all the excess, that the legacy carbon dioxide that's up there. Regenerative agriculture, and I'm not going to deal with, but rock weathering is one of the things that has been talked about. You can see at the bottom left here, here's a farm which is actually spreading rock dust on this field, and it actually does increase the viability of that soil. Unfortunately, what rock weathering requires is mining of rocks, which you see at the top left there, and the grinding of rocks to make the dust. And that's a major cost and a disadvantage. Then direct air capture has pluses and minuses. This is the first of its kind in Iceland. And you can see there are a whole bunch of fans there that are taking air, the same kind of air that you and I are breathing now, with 0.04% carbon dioxide concentration, taking that 0.4% out. And I'll show you exactly how that's done. Actually, in a minute. One of the advantages of this is it's permanent. I'll show you how in a minute. It's measurable, yes, and it's scalable. And in fact, it's also very expensive. So it's $500 to $1,000 per ton of carbon dioxide removal. It's easily the most expensive way to take this carbon dioxide out. But now there are 100 of these direct air capture units worldwide. And why? It's because most are funded by carbon offsets. People are prepared to say, I'll pay money as long as I can still pollute. Those carbon offsets are funding the extra more than 100 of these units. And this is how it works. So you can imagine that there's a big expense here, and not only getting the fan and all the other parts of this thing. Fans draw in the air, the filter out the CO2, the filter is heated, that's another cost. and then it's stored. What to do with it? What to do with all that carbon dioxide? Well, here are some ideas that the oil companies particularly like. You can hide it in deep saline water. You can use it for enhanced recovery of oil or natural gas. You can put it in depleted oil gas reservoirs, unminable coal seams. You can recover methane from coal seams, buried coal seams, and the etc. down at on the right-hand side is what they're doing in Iceland. They put it down into the basaltic rock that underlies that direct air capture filter thing, and it converts the calcium and magnesium minerals of the basalt into a limestone and a dolomite, of course. So next. So now we're going to ocean, and you see we changed the color to blue. This is one of the ocean climate facts that many people don't really realize. And that is that 90% of the extra heat that the legacy carbon dioxide and methane has put up there has gone into the oceans. And of course, thanks to your friend and mine, Sean, he's put this graph together that shows the 1982 to 2011 mean with the blue arrow there. And it also shows the that 2023, that's last year's heat of daily sea surface temperatures worldwide combined into that graph, which shows that the sea surface temperatures were going up remarkably just last year, and 2024 in the black is going up again. It's scary. No wonder we're getting bigger hurricanes. Here's another kind of ocean climate fact, and that is acidity. So at the same time as the carbon dioxide in air is going up on the red Keeling curve here, so in the pale green just below it is the ocean carbon dioxide concentration. Apparently about 30 or 35% of the carbon dioxide that's in the air, that gets into the air, goes into the ocean. There's an exchange back and forth. The bad news about the carbon dioxide going in the ocean is that the pH decreases. It gets more acid. And here we are, and this graph only goes to 2018 or thereabouts. If you extend that graph and we consider business as usual, the pH could go down to 7.7 by 2100. Now that's not ouch so much for us, but it's certainly ouch for a coccolith that can't secrete its skeleton. It's certainly an ouch for any other shelled organism in the ocean. Another ocean climate fact, and that is the layering of the ocean. Now, obviously, the temperature is not 55 worldwide, but it's considerably warmer at the ocean surface. There's a layer about 200 meters thick. And the problem with that is that in the tropics, any phytoplankton that get to grow in the tropics sink down there, and they sink down with the nutrients. And so the surface layer is almost devoid of nutrients. And so it's very difficult to get photosynthesis to go on, at least in tropical oceans. And then on a different kind of picture here shows the red rings here are the biosphere and soils. This is how long you can expect carbon dioxide to be stored in wood and in soils. And in the surface ocean, something similar, between a year and 100 years, maybe. As you go further down in the ocean, you can expect the carbon dioxide to be stored for longer. And of course, if you bury it in the Earth's crust, like, for instance, oil and gas reservoirs, it goes there for millions of years. But when you think of it, we're burning carbon dioxide that's been stored there for millions of years, and clearly that's a problem. So here are some ways that we can deal with it, perhaps. This is a seaweed arrays. So on the left, here's a fellow who's actually growing seaweed on some kind of a cable, probably off the coast of Maine. And that cable, that seaweed is brought in and harvested and used for many of the things that you and I eat or use for face cream or toothpaste or whatever it is that they use it for. Running Tide is a company based in Maine that is making carbon buoys out of wood chips and seeding them with seaweed. And the idea is that the carbon buoy would be going in an area where there are nutrients for the seaweed to grow in. And the carbon buoy, when it gets saturated with water and too heavy to float, would sink to the bottom of the ocean. And that carbon dioxide that was stored in that seaweed would then stay at the bottom of the ocean. Here's another company based in London, Seafields, that is harvesting seaweed that's on that ruins many a tropical island beach, harvesting that and either using it for biofertilizer or biofuels, or else putting it into something heavy and sinking it in the deep ocean. That's particularly with sargassum. So here's something that many of you may have heard of: ocean ion fertilization, sometimes called OIF. So there's a biologist by the name of Redfield who figured out that the ratio of nutrients necessary for photosynthesis of any kind is this. So for every 1 part of phosphorus, you need 16 parts of nitrogen and 106 parts of carbon and some. So the carbon comes from carbon dioxide. The nitrogen and the phosphorus are common nutrients in the ocean, in some parts of the ocean, but iron is needed in a tiny amount. And that is basically the essence of iron fertilization of the oceans, which I'm going to get into next. So here's a map of the oceans that shows in color, that's the yellow and the orange, areas that are nitrate rich, but chlorophyll poor. And it's been thought that those are areas that if you fertilize with iron, just iron, there might be enough phosphorus and nitrogen to produce a phytoplankton bloom, and we'll get to that in a minute. And the white cross and the green cross and the red cross are experiments that have been done with iron fertilization of the ocean in various parts of the world. And anyway, we'll go on. Here's how ocean iron fertilization is supposed to work. It helps the phytoplankton, which are of course at the base of the food chain, that feed the zooplankton, which get eaten by little fish and then bigger fish and perhaps whales. And some of these would fall to the bottom of the ocean. Now, how do we know that that might happen? How do we know how much how much would sink to the bottom of the ocean? How effective is this going to be? And the answer is we don't really know yet, but maybe there's a clue from the eruption of Mount Pinatubo. Mount Pinatubo looks like this now. It's clearly blown its top, and here it is blowing its top. There's an enormous amount of dust coming out of that volcano and landing on the ocean. And then there was a funny thing happened. So here's the Keeling curve, and Mount Pinatubo's eruption is that funny little yellow, let's see if I can point to it. Yeah, this little yellow triangle. It happened in 1991, and it caused a leveling off of the Keeling curve that lasted for a couple of years. And if you calculate that out, it seems to have taken care of 20 gigatons, billions of tons of carbon dioxide. And why do we think that's significant? Well, we're wondering about this. And of course, you guys should know more about this than I will, but you recognize perhaps that these are glacial periods. Oops. Oh, beg your pardon. I'm going too fast here. The gray areas on this this graph are glacial periods with lower temperatures and lower carbon dioxide. But how is the carbon dioxide getting down to be so low? What is the cause of the reduction in carbon dioxide that took place during every glaciation, as well as the lowering of the temperature? And one of the peculiar things is that it's associated in these cases with an increase in dust, as seen from many ice cores. This happens to be a result from one of those ice cores. So maybe the dust was actually causing the reduction in carbon dioxide because of this ocean iron fertilization in a natural sense. Coastal blue carbon is what you often hear about that we need to put more carbon dioxide in seagrass, mangroves, and salt marshes. What worries me is that all of these are going to suffer from sea level rise. But that's one of the eyes. So many of you probably haven't come across this Ocean Visions. It's a nonprofit that is a kind of informal get together of many of these ocean organizations and universities around the country. You can see Woods Hole on the top right. MIT is halfway down on the right. Any number of others, University of South Florida, Santa Barbara is in there, Georgia Tech. Anyway, these are organizations that are really working on various ways in which ways in which the ocean can be used to reduce carbon dioxide in both oceans and air. So then we go to enhanced atmospheric methane oxidation. So where does methane occur worldwide here? So that this is a map of the concentration of methane that you see in various parts of the world. And you recognize the Texas and western Pennsylvania with its source of methane, natural gas. There's also up in northern part of the western Siberia, which is where the gas wells are in Russia. And all the rest is basically methane use or methane coming from rice paddies and all kinds of other sources of methane. So here is obviously a big source of a big potential source of methane. This is, these are the areas of frozen wetlands, permafrost, and the brown areas are where the permafrost is on land, and the green areas just, for instance, off the northern coast of Russia, is where permafrost is actually underwater, because during the last ice age, sea level was 400 feet down, and so it was then land. And here's a picture of what you see, methane bubbling up from the bottom of the ocean off northern Russia. And here's a proposed solution for enhanced atmospheric methane oxidation. Natural sea salt spray is always there. Iron, perhaps added to the combustion gases of this ship, forms iron chloride, which oxidizes the methane. And this is sometimes also known as iron salt aerosol. I'm not suggesting that this or any other of the methods that I've given here are the best or the only methods. These are ones that are being worked on in various ways. Oh yes, and here are some others. Carbon negative concrete. So you're probably aware that the making of cement by heating up limestone in that is crushed limestone in up to, I think it's 1400 degrees, is and also producing a lot of carbon dioxide emissions. I think it amounts to something like 8% of our emissions go into making cement. Brimstone is a company in existence now that is making this low carbon negative cement. And here's another one, Blue Planet Systems is making limestone aggregate from the carbon dioxide in the air, as well as a source of calcium, of course. I'm not suggesting that these are the best ways, but these are two of the ways that have actually spawned companies. So it transforms the problem into a solution, because of course we use a lot of cement and make a lot of concrete. It's the most used product beyond water by humans. Okay, sequestering 25 billion tons of carbon dioxide per year will pay for itself with that market. Federal, state, and local procurement laws accelerate development. So some states in the US have actually urged that all of at least that the state works use this concrete, and I think more is coming. And okay, where do we go from here? Or where does this come from? There's a fellow by the name of Peter Fikowski. He's actually a physicist, and he put together all these things in this book. I can recommend it. It's a good read, and he also says that there's a lot more coming. And here he's also put together a lot of climate restoration working papers, which are very well written, and they show that the various methods that I've given you in this talk here vary enormously in cost. So the cost of ocean iron fertilization is relatively cheap. I mean, it's really cheap, whereas the direct capture of carbon with the machines that I showed you an example of in Iceland is very expensive. So what are we going to do? What are you going to do about this? So this is what I want you to hold in mind as you think, what am I going to do? What will be our bequest and legacy for future generations? How can I work on making things happen in this area? First of all, we have to recognize that net zero isn't enough to hold the climate. Massive greenhouse gas removal policies are urgently needed. That business, scientists, and entrepreneurs want in on this. I realize it's not the part of the mission of this the Climate Change Institute, but certainly some parts of the university could be helping in this. And yeah, climate change is $1 trillion opportunity disguised as an existential threat. Isn't that something? Setting a goal of climate restoration will be a framing home run. So in other words, if we put it out there that this is what we need to do, maybe that's a good frame and could enable successful bipartisan climate policy. I hope so. Your task to champion climate restoration as a term and promote specific ways, support greenhouse gas removal legislation, such as the CREST Act, like I mentioned earlier, and promote the research and development that needs doing. And here, my teams, I happen to work with Citizens Climate Lobby and its greenhouse gas removal action team, which has this wonderful acronym. And there you go. Thank you. All right. Any questions from, can we get questions from the audience online? Okay. Yep. Anyone's here? Yes.
It's a politically loaded statement, but in our present environment with Republicans and Democrats, what hope do you hold out that it'll be bipartisan?
My hope is with Senators Collins and Cantwell, and not just those. There are it's the CREST Act now has five sponsors and co-sponsors, and 2 of them are Republicans, 2 are Democrats, and then there's Angus King. And my hope is that this makes such a lot of sense when you finally realize that we've got to do something. Otherwise, the other choice is climate consternation. How much we're kind of up against something here where we have to pose 2 complete opposites here. One is climate restoration, it's those beautiful kids that I showed near the end here, and the other is that we have to expect more of the same, much more of the same, and the one is so different from the other. But I don't have an answer for your your question. I've got my fingers crossed, as probably you do too. One of the books that we've got to deal with is Reclaiming Our Democracy by a fellow by the name of Sam Daly Harris. And I bet I know he's going around the country telling people about the need for democracy. But on the other hand, you notice that the Republican Party has almost entirely gone over to Donald Trump, who doesn't believe any of this stuff.
It's
So,
terrifying.
it's terrifying. Yeah.
Hope you're right.
You might be interested to know that our civil engineering department here, in fact, our College of Engineering is actively involved in a number of these ventures that you're talking about.
Really?
Yeah, they've had people for several years now who are working on concrete that it requires much less carbon combustion,
Yes.
and people who are working on, lifetime costs, energy and carbon costs of products and things like that. And it's been on their radar for some time. So they're doing good work.
Great. Thank you. All right.
Dan's online and he has a question for you. Go ahead, Dan.
Hi, Peter. I was wondering if could you go back to the graph that showed the cumulative carbon in the atmosphere, the red bars and the yellow bars.
Okay. Just a minute. That came quite early on.
Just go backwards real fast. That'll be the quickest way to do it.
Okay.
It was about halfway through.
Oh, but was it that one?
No,
No, keep going, keep going, keep going,
you're getting
keep
close.
going.
Go on.
Few more. Oh, a few more, few more.
That one.
Yeah,
This one,
that one.
this one. To me, this is one of the scariest graphs that you showed in the whole presentation, because it really shows the scale of the problem.
Yes.
And so I was wondering, my question is, all of those solutions, like carbon removal techniques, has there been a study done that you know of that looks at how the amount of scaling that would be required for those kind of things? Because in particular, I've been interested in the carbon capture and removal efforts that are going on in Iceland.
Yes.
Even though Iceland has this plentiful geothermal energy, which isn't limitless, but there's a lot of it.
Yes.
Even with that sort of green and plentiful energy they have, it's still $1,000 a ton.
Yes.
Which is way out of anyone's price range. I mean, I'm thinking about carbon offsets for the campus here, and when they went up from $3 a ton to $10 a ton, it almost made it blew the project out of the water. We basically can't afford to do it if the carbon offsets are in the $10 to $20 a ton range. So at $1,000 a ton, it's challenging. I just wondered if you had seen any studies on the actual feasibility of scaling up those carbon capture and removal techniques.
No, I haven't. I happen to know that I only recently found out that there were more than 100 direct air capture companies out there now. I don't know how many of the facilities, somewhat like Iceland's, have been built and are in operation. I don't know that. It's as you can imagine, it's kind of a rapidly changing field. But
Yeah.
the oil companies and gas companies, they certainly like the idea of carbon offsets in order to fund these. Yeah.
Peter, can I ask a question?
Yes, go ahead.
This is Ron Davis.
Hi, Ron.
You emphasized changes that can be made on a worldwide scale, institutionally, commercially, etc., but didn't say a word about changes in individual behavior. And apart from individuals lobbying their legislators, there's also the possibility that enough people could change their behavior and shift their use of carbon to more renewable sources to have some influence over the changes that we need. Would you comment as to whether that approach can also be of some importance?
Yes, it is definitely, and it's what we're doing now. We're now in the paradigm that you remember, perhaps burn less now, and many of us are really working on this. But in the end, what we're working on is making the yellow bars on this graph that is on the screen now smaller, which is very important. It's valuable, but it doesn't deal with the tall red bars above them. And so it's allied. It certainly puts you in the right kind of frame of mind. You're right, Ron, on that. And I wish it were more effective in getting the tall red bars down. That answer your question?
More or less. I'm just wondering whether the sum total of personal action can have a major impact. And I was thinking that we need some numbers on that.
Got it. It certainly makes a major impact in getting the yellow bars on this graph smaller and smaller year after year. Yes. What the essence of that presentation was basically a focus on the tall red bars.
Dan asked.
Peter?
There's a
Peter?
couple questions up there.
Yeah. Yes.
Peter, this is David Kuhnhart from
Oh,
Scarborough.
hi, David.
And,
yes.
and thank you so much for bringing these things forward, particularly the concepts in the slide that you have remaining up. One of the other questions in the chat was, how can we avoid the capture of carbon and its sequestration from being an excuse for oil and gas companies to keep doing their business? And that is a logical, let's say, moral hazard. But the graph that you have up there right now proves that we must do all of the above. We must require those who are pulling carbon dioxide out of the ground to reduce their action. And that's most effectively done by putting a price on carbon, as you and we have agreed for a number of years. But then we've got to go beyond that. And we really have to start collaborating, even with oil and gas companies who, after all, have pumping technology down solid to reverse the flow and put carbon dioxide back underground. And I want to repeat what you said. There are now over 120 companies that are doing this in a lot of different ways. And the possibility of scaling up is, I think, embedded in the funding of their research and development. The CREST Act is a good way to start. There's another bill that's live in both the House and the Senate, which would put about 200 times more money than the CREST Act into research and development on all strategies for carbon dioxide removal It's called the Carbon Dioxide Removal Research and Development Act, both in the House and the Senate. I also want to address one of the very first question about what is the prospect of the present Congress of doing anything. Interestingly, in the House, there is a Republicans-only Conservative Climate Solutions Caucus that now has 82 members. That's more members than in the Freedom Caucus. It is a very going concern, even in the present House, that we look at a lot of different solutions. So I think this is a very fruitful field. Thank you for bringing it forward and discussing it.
And thank you, David. You're so expressive. I can't add anything to that. Thank you.
Somebody else has their hand up too. I'm not sure who it is. Oh, Susan.
Okay, who's next? With a hand up?
Hi, Peter.
Hi.
It's Sue Connard. How are you?
Oh, hi.
One of the things you didn't really mention is the potential for agriculture to enhance carbon sequestration. And we have converted so much of our natural forests and wildlands to agricultural land. It seems to me there's tremendous potential for changing agricultural techniques in a way that both decrease nitrogen use from, which is very costly in terms of carbon, and increase soil storage of carbon. Do you have any information on that or comments on that?
Well, my only comment is whatever any of us have to say about that should go into urging our members of Congress, but particularly Shelley Pingree, who's very much involved in the farm bill, which needs to be passed by the end of this year. And I agree. It's an important angle that we can definitely work on. Thank you. Oh, we've got I can't see who's next or who's in the chat, but Rebecca, can you read that?
I think you can.
Oh.
Oh, maybe not. I can just read it to you.
Okay.
It says, this is from Cindy Eisenhower. It says, to what extent do you worry that CCS provides the opportunity for the petrochemical industry, petroleum states to delay migration action? That's the question. And then she says, CCS is deeply supported by the oil and gas industries.
Mitigation?
Yes.
I think, probably.
Yes.
Oh, sorry.
CCS is carbon capture and storage, for those of you who don't know. And you remember the picture that I had of all of the ways that the oil and gas industry have of storing the carbon dioxide that they capture. And this is what one of the things that David Kuhnhart just a minute or two ago emphasized, that if there's a way that we can involve the skills of the oil and gas industry in understanding that their industries and all of us, by the way, have been the cause of this excess carbon dioxide and methane and other things in the atmosphere, they also have a lot of the skills that we'll need to deal with it. And we'd like to put them to work in whatever way you can think of.
If I may chime in again, Peter.
Hi, Ron.
One of the tragedies in our modern wasteful economy is all of the organic matter that is exported in our garbage and goes into landfills where it is turned into methane and carbon dioxide. And I think there's been some substantial but limited success in getting people to recycle their plastics. Why not have and the United States is a particular problem in the waste of organic matter, carbon containing, of course. Why not a program now to add to the recycling of plastics that would recycle organic matter, and each home have a bin for their organic waste, and that be collected and returned to agricultural lands.
Yes, you have a very good point, and that is being done by some towns. The problem, as I see it, is a problem that we often don't think of. But consider yourself and myself, and everybody basically is an addict to the benefits of fossil fuels. It's the I drove here from my hometown in Winslow up to Orono, and I had to buy gas at the gas station. And I thought, what is this? I'm part of the deal. I'm part of the problem. And other people who are using plastics, you pointed out plastics and organic wastes, they don't see that as being a problem. And so one of the things that we all have to do is to recognize that and say that. You probably haven't heard too many talks like I've just given you here that point out how big these red bars are and how it'll take all of the intelligence of human beings to reduce that. And it won't be just the technologists. It'll be all of us dealing with the kinds of issues you just mentioned. Thank you.
Peter,
Yes.
with the red bars there, that's a model.
Yeah.
And how much do you have to actually decrease? Well, back up. Our present climate is totally out of control now, and there are positive feedbacks that are making things worse.
Yes.
And so steady state is not an option either.
Right.
How rapidly do you think we need to change our emissions more negative to get the red bars into a decay mode? Because we don't have 10 years to wait.
Right.
We don't have 5 years to wait.
Right. So the author of this book, Climate Restoration, is an optimist, and he thinks that we can get, with ocean iron fertilization in particular, we can get a whole bunch of that extra carbon dioxide down at the bottom of the ocean, with using only a small percentage. It's just a few percent of the ocean surface to do that work. Now, there are plenty of people who think that he's a wild optimist, but he has some rationale in there, and I would welcome you reading that and seeing what you think about how it can be done, whether it can be done.
I did read the book, actually.
You did, okay.
And it doesn't look feasible.
Yeah,
It doesn't look feasible.
there are.
It could be one of many feasible things that
Yes.
contribute collectively
Yes.
to that problem.
Peter, Dan's earlier question about these red bars and the scale is the crux of the issue, of course. And we do talk about this all the time. I mean,
Yes.
we're well aware of this. And just to illustrate the challenges. Clearly, if we could find ways to remove that old anthropogenic carbon, you call it the legacy carbon,
Yeah.
that's a good name, from the atmosphere in quantities, and as Steve says, soon, it would be great. But the scale is something else.
Yeah.
And one of the things I've read is, this was from some work some years ago on this topic, was that if we remove all carbon emissions from 1 year during the year, just the human contribution,
That's okay.
using the crushed basalt, more
Yeah,
or less,
okay.
method, the amount of material created by that conversion would fill Lake Huron.
Goodness.
1 year. That's
Goodness.
just this year's. And another example I always remember comes from one of John McPhee's wonderful books. They're all wonderful, but he wrote one about modes of transportation about 20 or 30 years ago. And he talks about railroad coal trains that go from Wyoming, where there's low sulfur coal, out down to a large power plant near Atlanta that actually has 2 power generation systems in the same place. But the trains are each a mile and a half long. They don't even stop at either end. They are filled as they drive by the spot in Wyoming, and they're emptied as they drive by Atlanta. And it takes 5 1.5 mile long trains every week to run those things. And so that's the
That's
mass.
one power plant.
Well, there are 2 there, but
Okay.
it's a large, but that's just one place in the world. And so it's a massive amount of material, just the scale of the material itself that of course gets combusted and produces all that CO2. But the CO2 can't come out of the air without having some form, solid form, that's the point. And it has to be of that scale just for that one place. So these are
Wow.
striking challenges. And but desperately needed. So it's wonderful that there are companies working hard to try to figure out how to do this, and obviously they're working to scale it up, I'm sure. But and make it affordable, but it's seems like about the only way we can make progress on this part. You know, there have been engineering proposals to put change the chemistry of the stratosphere in such a way to reduce the solar input to Earth, which would cool it, so that could counteract some of the actual effects, possibly. But you know, whether that can even be done and not cause other problems is doubtful. It's very hard to, as Garrett Hardin once put it, we can never do only one thing, because everything we do affects something else that we didn't anticipate. That's in ecological systems, but it's true
Indeed.
in most systems.
Indeed.
So I mean, I don't mean to say all this to be discouraging, but just to be realistic about where we really are. And
Yes.
It's not only non-trivial, it's a huge challenge for humanity to do this, and it's urgent.
Yes.
It's urgent.
Yes. Yeah. Yeah. Yes. So Stephen, one thing that I didn't manage to put into this talk, but just where are we getting the over what period of time are we mining fossil fuels? It's an enormously long time. It's hundreds of millions of years, basically from, I don't know what the earliest oil and gas or coal deposits are, but it's at least back into the Carboniferous and Permian and so on.
That's right. That's 350 million years
Exactly.
probably.
It's what, and we're burning them at the rate you just,
And it's a
pointed out.
small fraction of what's in the earth.
yeah, right,
But
right,
it's been, what we've done is enough, and this was recognized, of course, long ago
yeah,
as a problem, when,
Yeah.
long before people could see the effects, but Svante Arrhenius, the
Yes.
famous chemist from Sweden, was giving lectures about this. You know, when it wasn't even his field, he was an electrochemist, but
indeed.
People before him were aware of this issue, so the physical issue has been well known, but nobody started to really pay enough attention soon enough to what we were doing, and you know, that red curve extends a long way to the left.
Yeah.
Unfortunately.
Hey,
Yes,
Peter,
yes.
Bill Fackenthal here. How are you?
Oh, Bill, hi.
Hey, could you go back a couple slides more to that one that you had that I think was very impressive? That's it.
That one.
I think if I read that right, I think that's one of the most scary slides of all.
Yes.
I mean, unless we actually just really get on this cumulative stuff.
Yes.
I mean, this other stuff down here looks like chicken feed, okay? And I don't think most people know that at all. They think if we get like taking some of the carbon out of the atmosphere, we'll be okay, but
Yeah.
we won't.
Exactly.
And I just think this chart is a wonderful chart. As bad as it is, it clearly lays it out.
Yes.
That's
Thank
all.
you. And then, of course, a little bit earlier than this, where are we? Yeah, this, well, that, that shows it, doesn't it?
Yeah.
The annual is tiny compared to
Right.
the cumulative,
And
yes,
the next
Yeah,
one goes, even if we reduce annual,
yes,
And that's 20 years.
cumulative still keeps growing. Go to the next one with,
yes,
oh, there you go. So
There you
even-
go. Okay, so I
even if
see,
we-
yeah. Mhm.
Even with reducing emissions, the
yes,
legacy keeps growing.
yes.
Yeah, yeah, right. Thank you.
Thanks. Thank you all for being on this call.
Thanks, Peter.
Thank you for putting it all together.
Okay.
All right,
Excellent.
Scary as it is.
scary as it is, yes.
This
Yeah.
one says, what role does nuclear energy play in reducing our appetite for fossil fuels?
Okay, one of the questions has come up about nuclear, and it's one of the forms of alternative energy to fossil fuels. And one of the advantages, of course, of nuclear is that it doesn't produce anything like any portion of these red bars, except in the manufacture of some of the equipment that you need for nuclear power plants. But I think my personal opinion is that we've become really very much afraid of nuclear because it's associated with bombs, of course, and we know that it has awful effects when it's a sudden eruption like that. But from the limited amount of reading that I've done about nuclear, I find that it would be far more acceptable if people really caught on to the problems of this particular graph here and the fossil fuels. This is, oh yes, another piece of reading I've done is how many people have actually been killed from nuclear power plants. And
None.
it's almost none. How many people have been killed from mining coal? Just the mining of the coal, let alone the burning of the coal. And people are not aware of those contrasts. So, who asked that? Was it you who asked that? Oh no, it was on
Question on the chat.
I don't know who it was, hold on.
we're having some technical difficulties here trying to
It was Albert Larson.
Albert Larson, thank you for asking that question, Albert.
One aspect of that question, which probably should be clarified, is that the two main types of renewable energy, wind and solar, that would play a major role, are good only when the sun is shining and the wind is blowing. And either some storage capacity for that energy is necessary to carry through the down periods, or a source of base energy to fill in the down periods is needed. And
Yes.
that is a major area where nuclear can play an important role.
Yes, thank you, Rob. Yes, indeed. Actually, one of the people who in Maine now, who has been very much involved in nuclear, knows the insides and outs of it, is the president, I think that's what he's called, of the Maine Maritime Academy. And one of the major so Maine Maritime Academy is mostly involved in training people how to operate transport ships. And it occurs to me that that one of the uses of nuclear power has been in powering nuclear submarines for the US and also aircraft carriers. And they've been doing that for 50 years without accident. And it occurred to me that Maine Maritime Academy could work with that to get much of the transport, the marine transport capacity converted to nuclear in the same kind of way. He hasn't picked up on that yet. He's happens to be a nuclear expert, so maybe he will.
David has his hand moved.
David.
I wanted to follow up on that. It happens that during COP28, the Conference of Parties in December, 25 nations agreed with this thought that has been suggested, that nuclear should be pursued, particularly advanced nuclear energy, smaller in scale, along the scale of engines in boats. And in fact, the Russians have already done this, and they have a boat that they built about 4 years ago that powers a city of about 200,000, not far from North Korea, from a ship. And so it is a feasible technology, and there are a number of countries who would like to pursue advancing that. The questions are cost and insurability. And those nuts have not been cracked yet.
Right. Thank you. Yes.
The last bombshell might be saying, well, what are you going to do about the growing population?
Yeah. Okay.
Which is the ultimate problem here.
Yes, yes, yes.
Nobody will touch that.
No, it's a difficult one to touch. And in
Peter?
fact, all of us benefit enormously from the healthcare services. For instance, I almost certainly wouldn't be alive now.
George and I wouldn't be either.
Yeah, right. Yeah. And and so when you go back in time, it was commonplace for babies to die. Unfortunately, I mean, obviously, but it would be rare for any family to raise half of its children to adulthood. And that would apply to any of us. It would also apply to the kings and queens and tsars and tsarinas of wherever you were. There was essentially no healthcare. And now there's healthcare at almost unlimited scale, at least for us, and in many parts of the world.
Peter Fikowski addresses population in his book, and he points out that if all countries had the same rate of children, of having children as Italy does today, which is 1.3 children per family, the level of population would go down dramatically. And by 2100, it would be significantly lower, obviously without dispatching of anybody. But empowering women and empowering family planning is an important ingredient in the solution.
Yes, indeed. Thank you.
It
Thanks.
is, unfortunately, we're not allowed to discuss reproduction in our political system.
Right.
Yeah, yeah. All right.
Thank you. Thank
Thank
you
you.
very much. for-
All right. Well,
Thanks, Peter.
I've got some thank yous here in person. Thank you all for showing up online.
Yes, thank you very much.
Thank you,
All
Peter.
right.
That was just great, a great session.
All right.
It did. Thank you very much.
Bye-bye.
Okay, see you, sir.